Imagine waking up tomorrow and discovering that Earth has vanished from its orbit. Not exploded, not destroyed, just no longer circling the sun. What would happen? Most people think the answer is obvious. Gravity would pull Earth straight into the sun. After all, the sun contains more than 99.8% of all the mass in the solar system. Its gravity controls the motions of planets, comets, asteroids, and even distant clouds of ice billions of kilometers away. So why doesn't Earth fall into it? Right now, at this very moment, the sun is pulling on every atom in your body. The force is enormous. The sun's gravity reaches across nearly 150 million kilometers of space and grips our entire planet without interruption. Yet, Earth never crashes. It never spirals inward. It never gets noticeably closer year after year. For more than 4 billion years, Earth has remained in a remarkably stable orbit around a star that outweighs it by a factor of more than 330,000. How is that possible? The answer seems simple at first. Many people learn in school that Earth keeps moving sideways while gravity pulls inward. The result is an orbit. But that explanation is only the beginning. Because once you ask a deeper question, the mystery becomes far stranger. Why does moving sideways prevent a fall? Why does gravity create circles and ellipses instead of collisions? Why can entire galaxies remain stable for billions of years without collapsing into their centers? And perhaps most importantly, what is a fall in the first place? As we journey from Newton's revolutionary insights to Einstein's curved spacetime, from planetary motion to the architecture of galaxies, we will discover that Earth is falling toward the sun right now. Constantly. Relentlessly. The reason it never reaches the sun reveals some of the deepest truths ever uncovered about the universe. And by the end, what seems like a simple question about our planet will lead us into a story involving invisible geometry, warped space-time, cosmic structure, and the very nature of motion itself. To understand why Earth does not fall into the sun, we must begin with something much more familiar: a falling object. Drop a stone from your hand. Immediately, it accelerates toward the ground. For thousands of years, this simple observation puzzled philosophers. Why do things fall? Ancient thinkers often assumed that objects naturally sought their proper place. Heavy objects belonged below. Light objects belonged above. The explanation felt intuitive. But intuition can be deceptive. In the 17th century, a profound transformation began. A generation of scientists started asking not merely what happens, but why. Among them was a remarkable English physicist and mathematician named Isaac Newton. According to a famous story, Newton observed an apple falling from a tree and wondered whether the same force that pulled the apple downward might also govern the motion of the moon. Whether the apple story happened exactly as described is debated by historians. What matters is the idea. Newton realized that the force causing an apple to fall might extend far beyond Earth. Perhaps gravity was not merely a terrestrial phenomenon. Perhaps it was universal. This was a radical thought. At the time, many people viewed celestial objects as fundamentally different from earthly ones. The heavens seemed perfect and eternal. Earth was messy and changeable. Newton erased that distinction. He proposed that the same physical laws apply everywhere. The force pulling an apple downward also pulls the moon toward Earth. The force holding the moon in orbit also acts between Earth and the sun. The force governing planets also governs distant stars. For the first time in history, the universe appeared unified. Newton expressed this insight through what became known as the law of universal gravitation. Every mass attracts every other mass. The strength of the attraction depends on two things: the masses involved and the distance between them. The larger the masses, the stronger the gravitational pull. The greater the distance, the weaker the pull. This simple principle transformed humanity's understanding of the cosmos. Suddenly, planetary motion no longer required mysterious celestial mechanisms. Gravity could explain it. But a challenge remained. If gravity pulls planets toward the sun, why don't they simply crash into? Newton approached this puzzle using a thought experiment that remains one of the most elegant in science. Imagine standing atop an impossibly tall mountain. You fire a cannonball horizontally. The cannonball moves forward while gravity pulls it downward. Eventually, it strikes the ground. Now fire it faster. It travels farther before hitting the ground. Fire it even faster. Farther still. Eventually, something remarkable happens. The surface of Earth curves away beneath the cannonball at exactly the same rate that gravity pulls it downward. The cannonball falls continuously, but the ground continuously curves away. Instead of hitting Earth, it keeps missing. The result is an orbit. This idea is one of the most important concepts in physics. An orbit is not the absence of falling.
An orbit is falling that never reaches the target. Earth is not resisting gravity. Earth is not escaping gravity. Earth is falling toward the sun every second of every day. The reason it never arrives is that it is moving sideways extraordinarily fast. Earth travels around the sun at approximately 30 kilometers per second. That is about 108,000 kilometers per hour. Fast enough to cross the United States in less than 3 minutes. Fast enough to travel from London to Tokyo in under 5 minutes. At this immense speed, Earth's path continually curves around the sun. Gravity bends the trajectory inward. Motion carries it forward. The result is an orbit. Yet even this explanation leaves unanswered questions. Why does gravity bend motion? Why do orbital paths form ellipses rather than perfect circles? Why are planetary systems stable at all? To answer those questions, we must look beyond Earth and examine the structure of the solar system itself.
The solar system appears calm and orderly. The planets move along predictable paths. Their positions can be calculated centuries into the future. But beneath this apparent simplicity lies an extraordinary gravitational dance. Every object influences every other object. Jupiter pulls on Saturn. Saturn pulls on Earth. Earth pulls on Mars. Even tiny asteroids contribute their own minute gravitational effects. The solar system is not a collection of isolated bodies orbiting a central star. It is a vast, interconnected network of gravitational relationships. The Sun dominates because of its immense mass. Containing roughly 99.86% of the solar system's mass, it acts as the primary gravitational anchor. Yet the planets are not passive participants. They also pull on the Sun. In fact, the Sun itself moves. Many people imagine the Sun remaining perfectly stationary while planets orbit around it. Reality is more subtle. Both Earth and the Sun orbit a shared center of mass. Because the Sun is vastly heavier, this point lies very close to the Sun's center. But it is not exactly at the center. The same principle becomes even more dramatic with Jupiter. Jupiter's immense mass causes the Sun to wobble noticeably as both objects orbit their common center of mass. This concept has become one of the most powerful tools in modern astronomy. When astronomers observe distant stars wobbling slightly, they can infer the presence of unseen planets. Many of the thousands of exoplanets discovered in recent decades were found using precisely this technique. A planet's gravity reveals itself through the motion it induces in its parent star. Gravity, therefore, does not merely govern motion. It becomes a messenger carrying information across vast cosmic distances. As scientists extended Newton's ideas beyond the solar system, they discovered that gravity organizes structures on scales almost impossible to comprehend. Stars gather into galaxies.
Galaxies gather into clusters. Clusters gather into superclusters. Filaments of matter stretch across hundreds of millions of light years, forming what astronomers call the cosmic web. Every level of this hierarchy is shaped by gravity. The same force that keeps your feet on the ground influences structures larger than anything the human mind evolved to visualize. Yet the deeper scientists looked, the stranger gravity became. By the 19th century, Newton's equations had achieved extraordinary success. They explained planetary motion with stunning accuracy. They predicted the return of comets. They enabled the discovery of entire planets. When irregularities appeared in the orbit of Uranus, astronomers used Newtonian gravity to calculate the location of an unseen world. That world turned out to be Neptune. It was one of the greatest triumphs in scientific history. And yet, gravity still concealed a secret that would force physicists to rethink space, time, motion, and reality itself.
Newton's explanation works extremely well for most of the solar system. It predicts planetary motion with astonishing accuracy, and even allowed astronomers to discover Neptune purely from mathematical irregularities. But there was a problem hidden in the orbit of Mercury. Mercury, the closest planet to the Sun, does something slightly strange. Its orbit slowly shifts over time. Most of this shift can be explained by Newton's gravity, but a tiny leftover motion could not be accounted for. This small discrepancy was only about 43 arcseconds per century, extremely small, but measurable. For decades, scientists tried everything. They searched for another hidden planet inside Mercury's orbit. They even proposed a ring of dust near the Sun. Nothing worked. Then, a new explanation arrived. A radical one. In the early 20th century, Albert Einstein proposed something that completely changed how we understand gravity. He said gravity is not a force in the traditional sense. Instead, gravity is the shape of space and time itself. This idea became the theory of general relativity. To understand what this means, we must remove a very old assumption.
Newton imagined space as a fixed, empty stage where objects move, and gravity acts as a force pulling them. Einstein replaced that stage. He said the stage itself is flexible. Mass and energy bend it, and objects move along that curvature. This structure is called space-time. In this picture, Earth is not being pulled toward the Sun. Instead, the Sun is bending space-time around it, and Earth is simply following the straightest possible path in that curved geometry. That straightest path is not a straight line in space. It is a geodesic, the equivalent of a straight line in curved space-time. So Earth is actually doing something very important. It is trying to move straight. But space-time itself is curved, so the path loops around the Sun. This is why Earth does not crash into the Sun. It is not resisting a force. It is not balancing forces. It is following geometry. This idea was confirmed in 1919 when observations during a solar eclipse showed that starlight bends as it passes near the Sun. This matched Einstein's predictions exactly, not Newton's. From that moment, gravity was no longer just a force. It became geometry. And this changes everything about the question we started with.
Because now, Earth is not orbiting in the classical sense. Earth is continuously falling through curved spacetime. There is no engine keeping it in orbit. There is no invisible tension pulling it outward. There is only geometry.
But this still raises a deeper question. If Earth is falling, why does it not eventually lose energy and spiral into the sun? The answer lies in a subtle property of orbital motion. In empty space, with no air resistance and almost no friction, motion does not naturally decay. Earth is essentially moving in a vacuum. There is nothing to slow it down. So once it is in orbit, it remains in orbit. But this stability is even deeper than that. It comes from the conservation laws of physics. Earth has angular momentum, a kind of rotational inertia that resists change in orbital motion. To fall into the sun, Earth would need to lose this angular momentum. But there is no mechanism in space large enough to remove it quickly. Only extremely slow processes exist, such as gravitational interactions with other bodies or very long-term tidal effects. On human timescales, and even geological timescales, Earth's orbit is effectively stable. However, stability does not mean permanence. The solar system is not perfectly static. Over billions of years, small gravitational nudges accumulate. Jupiter plays a major role here.
Its massive gravitational field subtly reshapes the orbits of other planets, including Earth. But even then, the system behaves like a carefully balanced, chaotic machine, stable in the short term, unpredictable in the extremely long term. Now we zoom out again, because Earth is not the only object orbiting something. Entire galaxies are held together by the same principles. Stars orbit the center of the Milky Way galaxy, which contains a supermassive black hole called Sagittarius A star. Yet here, something even stranger appears. Stars at the outer edges of galaxies orbit too fast. According to visible matter alone, galaxies should fly apart. But they do not. This is one of the strongest pieces of evidence for something we cannot see directly: dark matter. Galaxies appear to be embedded in enormous, invisible halos of mass that hold them together gravitationally. Without this hidden structure, the same physics that keeps Earth in orbit would fail at galactic scales. So the same question repeats itself at every level. Why don't things fall inward? Planets do not fall into stars. Stars do not fall into galactic centers. Galaxies do not collapse into clusters, and clusters do not collapse into single points. At each level, motion and gravity create balance through geometry, inertia, and hidden mass. Now we return to Earth again, but with a deeper understanding. Earth is not simply not falling into the sun. Earth is in a constant state of controlled gravitational freefall, guided by space-time geometry, stabilized by angular momentum, and embedded in a much larger cosmic structure shaped by both visible and invisible mass. And yet, even this is not the end of the story, because modern physics introduces another layer, one that challenges even the idea of space-time itself. At the smallest scales, space-time is not smooth. It fluctuates. It may be quantized. And at extreme conditions, such as inside black holes or at the beginning of the universe, our current understanding breaks down. This is where gravity is still incomplete.
Where general relativity and quantum physics do not yet fully agree, and where the true reason behind cosmic structure may still be hidden.
References for authenticity: Isaac Newton, Philosophiae Naturalis Principia Mathematica, 1687. Albert Einstein, General Relativity, 1915. Observational Confirmation, Eddington's 1919 Solar Eclipse Expedition.
When physicists say Earth is following a straight line in curved spacetime, that sounds almost like a metaphor. But in Einstein's theory, it is literal. The key idea is this: an object in motion with no external force always follows the path of maximum straightness allowed by spacetime. In flat space, that path is a straight line. But near a massive object like the sun, space-time is curved, so the straight line bends. This is why Earth's orbit is not a force-balanced circle, but a natural geometric trajectory. To see how deep this goes, imagine removing the sun instantly. In Newton's picture, Earth would suddenly fly off in a straight line because gravity disappears. In Einstein's picture, something more precise happens. Space-time becomes flat again, and Earth continues along its geodesic, which now appears as a straight line in space. So motion is never stopped or held. It is always continuation of geometry. Now here is the deeper twist. In general relativity, gravity does not act through space. Gravity is space-time itself responding to energy and mass. This means Earth is not orbiting in space. Earth is orbiting through space-time geometry that is being continuously reshaped by the sun. This leads to a very important consequence. There is no absolute downward direction toward the sun in the way people imagine. Instead, all directions are locally straight, but globally curved. That is why Earth never spirals inward under normal conditions. But now we push further. If space-time is geometry, then what determines its exact shape? Einstein's field equations give the answer.
Matter and energy tell space-time how to curve, and space-time tells matter how to move. But the equation is not simple. It is highly nonlinear. This nonlinearity is what makes the universe complex. It allows stable orbits, chaotic three-body systems, galaxy formation, gravitational waves. Speaking of gravitational waves, this is where things become even more real. In 2015, scientists detected ripples in space-time caused by colliding black holes, observed by LIGO Scientific Collaboration. These waves are literally distortions in the geometry Earth is moving through. So even space-time itself is not static. It moves, vibrates, and carries energy. Now return to Earth and the sun. Earth is not just orbiting a fixed curve.
It is moving through a dynamic gravitational landscape where space-time is slightly changing every second. The sun itself emits radiation, loses mass slowly, and interacts gravitationally with planets. So the track Earth follows is not carved in stone. It evolves slowly over time. This leads to a deeper insight. An orbit is not a perfect circle drawn once. An orbit is a continuously recalculated geodesic through shifting geometry. Now let's go even deeper into galaxies. Earlier, we said stars orbit galactic centers. But galaxies are not rigid structures. They are dynamic gravitational systems where billions of stars interact simultaneously. Each star follows its own geodesic in the galaxy's curved spacetime, but that curvature is shaped by visible matter, stars, gas, dust, invisible mass, dark matter, and overall galactic motion. This creates spiral structure. But here is the strange part. Spiral arms are not fixed structures. They are density waves. Stars enter and exit them. The spiral pattern is more like a traffic jam in space than a physical object. So even at galactic scale, orbiting is not simple circular motion. It is collective motion in a gravitational field shaped by hidden structure. Now zoom out further. Galaxies themselves orbit inside galaxy clusters. Clusters are bound by even larger dark matter structures. And those clusters are part of the cosmic web, a vast filamentary structure spanning hundreds of millions of light years. At this scale, gravity behaves differently again. Not because the laws change, but because initial quantum fluctuations in the early universe were stretched to cosmic size during expansion.
This is supported by observations of the cosmic microwave background, measured by missions like Planck collaboration. These tiny early density variations eventually became galaxies, clusters, and voids. So the reason Earth does not fall into the sun is not an isolated phenomenon. It is one expression of a universal rule. Matter moves along geometry shaped by other matter. Now we return to Earth one final time, but with all layers combined. Earth is falling toward the sun continuously, moving sideways at extreme speed, following a curved space-time geodesic, stabilized by angular momentum, embedded in a gravitationally evolving solar system, influenced weakly by all other planets, and part of a galaxy shaped by dark matter. So the real answer is not Earth does not fall. The real answer is Earth is falling, but the universe itself is structured in such a way that falling becomes endless motion instead of collision. Now we go even deeper into a subtle but profound point. Why does falling exist at all? Why does space-time allow geodesics that loop instead of terminating? Why does gravity not simply pull everything into a single point? This is where modern physics begins to intersect with unsolved problems. Because while general relativity explains the motion extremely well, it does not explain why space-time has the properties it does. And at quantum scales, gravity may not even be smooth. Some approaches to quantum gravity suggest space-time could be discrete, like pixels. Others suggest it emerges from deeper information-based structures. But none of these are experimentally confirmed yet.
This is why gravity remains the least understood fundamental interaction. We can calculate its effects with extreme precision, but its deepest origin is still unknown. And that brings us back to the original question. Why doesn't Earth fall into the sun? Because falling is not a movement toward an endpoint. It is a continuous tracing of geometry through a dynamic space-time structure shaped by mass, energy, and the hidden architecture of the cosmos. Earth is not avoiding the sun. Earth is following the only path space-time allows it to take. And that path loops forever, unless something disturbs it. References: Albert Einstein, General Relativity, 1915. LIGO Scientific Collaboration, First Detection of Gravitational Waves, 2015. Planck Collaboration, CMB Anisotropy Mapping, 2013 to 2018.
Now we arrive at a point where the original question begins to transform into something much bigger. Because the more deeply physicists studied gravity, the more they realized that the mystery is not why Earth does not fall into the sun. The deeper mystery is why anything can orbit anything at all. Why does the universe permit stable motion? Why can structures survive for billions of years? Why did the solar system not collapse shortly after its formation? And why are galaxies, stars, planets, and even atoms capable of existing long enough for life to emerge? To appreciate how remarkable this is, imagine an alternative universe. Suppose gravity were slightly stronger. Not 10 times stronger. Not 100 times stronger. Just slightly stronger relative to the other fundamental forces. The consequences would be enormous. Stars would burn faster, planetary systems would become less stable, galaxies would evolve differently, the entire history of the cosmos could change. Physicists often describe gravity as the weakest of the known fundamental interactions. The electromagnetic force between two electrons exceeds their gravitational attraction by approximately 10 to the 42 times. This difference is so enormous that it remains one of the greatest unsolved puzzles in theoretical physics. Known as the hierarchy problem, it asks why gravity is extraordinarily weak compared with other forces. Ironically, gravity's weakness may be one reason complex structures exist. If gravity were much stronger, long-lived stable systems might be impossible. Yet despite being weak, gravity dominates the largest scales in existence. Why? Because gravity only attracts. Electromagnetic forces can attract or repel. Positive and negative charges often cancel each other. Gravity has no negative mass equivalent. Every star contributes. Every planet contributes. Every galaxy contributes. Over vast distances, gravity accumulates. And because of that accumulation, the largest structures in the universe become gravitational structures. This fact leads us into one of the most extraordinary stories in modern cosmology. The story begins shortly after the Big Bang. Roughly 13.8 billion years ago, the observable universe was far hotter, denser, and more uniform than it is today. Measurements of the cosmic microwave background reveal something astonishing. The early universe was incredibly smooth. Temperature variations were only about 1 part in 100,000.
That means the young universe was almost perfectly uniform. And yet today we see galaxies, clusters, stars, planets, and people. How did complexity emerge from near uniformity? The answer appears to lie in tiny primordial fluctuations. Quantum fluctuations. At first glance, this seems impossible. Quantum mechanics usually governs microscopic particles. Galaxies are enormous. How could quantum effects influence cosmic structure? The answer may involve one of the most remarkable ideas ever proposed: cosmic inflation. According to inflationary theory, championed by physicists such as Alan Guth and later expanded by many others, the early universe underwent an astonishing burst of expansion. For an unimaginably brief moment, space expanded exponentially. Tiny quantum fluctuations were stretched to astronomical scales. Those fluctuations became slight variations in density. Gravity amplified those variations over billions of years. The denser regions attracted more matter. More matter created stronger gravity. Stronger gravity attracted even more matter. This process continued until enormous structures emerged.
In a very real sense, every galaxy may trace its existence back to microscopic quantum fluctuations that occurred when the universe was less than a second old. That means Earth's orbit around the Sun is indirectly connected to events that occurred near the beginning of cosmic history. The solar system exists because stars formed. Stars formed because galaxies formed. Galaxies formed because gravity amplified density fluctuations. Density fluctuations may have originated from quantum processes during inflation. The chain stretches from planetary motion all the way back to the earliest moments of known cosmic history. Now consider something even stranger. Gravity is continuously trying to create order and disorder simultaneously. Locally, gravity creates structure. Stars, planets, galaxies, clusters. But globally, gravity often increases entropy. This sounds contradictory, yet it lies at the heart of modern thermodynamics and cosmology. When a cloud of gas collapses under gravity, it appears to become more organized. But during collapse, enormous amounts of energy are released. Heat increases, radiation is emitted. Overall entropy rises.
The universe gains disorder even while local structures emerge. This subtle relationship between gravity and entropy remains one of the deepest topics in theoretical physics. It becomes even more mysterious when black holes enter the story. Black holes are often described as cosmic vacuum cleaners. This image is misleading. If the sun were magically replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. The gravitational field at Earth's distance would be nearly unchanged. This surprises many people. It reveals something important.
Gravity depends primarily on mass, distance, energy, and geometry, not on whether an object is a star or a black hole. What changes near a black hole is the geometry of space-time itself. As one approaches the event horizon, space-time curvature becomes extreme. Paths that once escaped begin to converge inward. Beyond a certain boundary, every future directed path leads deeper into the black hole. In a sense, the geometry becomes so distorted that escape is no longer a valid direction. This realization transformed black holes from mathematical curiosities into profound physical objects. Gravitational collapse naturally arises from Einstein's equations. Black holes possess thermodynamic properties. They have entropy. They have temperature. They can even evaporate through quantum effects. This was shocking. Until then, gravity and quantum mechanics were largely separate domains. Black holes force them together, and where they meet, our understanding begins to break. Inside a black hole, general relativity predicts a singularity, a region where known equations cease to provide meaningful answers.
Infinite density, infinite curvature, infinite breakdown. Most physicists believe these infinities indicate not physical reality, but incomplete theory. Nature is likely doing something more subtle. Yet, we do not know what. This ignorance points directly toward one of the greatest unsolved problems in science: quantum gravity. General relativity describes gravity extraordinarily well on large scales. Quantum mechanics describes particles extraordinarily well on small scales. Both theories have been tested repeatedly. Both work, yet they are mathematically incompatible in extreme conditions. At the center of black holes, near the beginning of the universe, perhaps at the deepest level of reality itself. Some researchers pursue string theory. Others investigate loop quantum gravity. Others explore emergent spacetime models. Still others propose that spacetime itself may arise from quantum information. The surprising thing is that many modern approaches suggest spacetime may not be fundamental. It may emerge from something deeper. This possibility would radically alter the meaning of our original question. Because if spacetime is emergent, then Earth's orbit is not merely a path through geometry. It may be a path through a geometry that itself emerges from more fundamental informational structures.
Some physicists have even suggested that gravity could be an emergent phenomenon, rather than a fundamental force. Ideas associated with researchers such as Eric Verlinde explore this possibility. These concepts remain speculative, but they demonstrate how far the question reaches. We began by asking why Earth does not fall into the sun. Now we are questioning whether space-time itself is fundamental. And the deeper we look, the more astonishing the situation becomes. Because every second of every day, Earth travels roughly 30 kilometers through space. At the same time, the solar system orbits the center of the Milky Way at approximately 220 kilometers per second. Meanwhile, the Milky Way moves through the local group. The local group moves relative to surrounding cosmic structures. Nothing is stationary. Everything is moving. Everything is orbiting. Everything is participating in an immense cosmic choreography governed by geometry, energy, and laws whose deepest origins remain unknown. From our perspective on Earth's surface, the ground feels solid and motionless. Yet in reality, we occupy a planet that is continuously falling, continuously moving, continuously tracing a path through a universe that is itself evolving. And perhaps the most extraordinary fact is this. The same equations that describe Earth's orbit also describe the motions of binary stars, the dynamics of galaxies, the trajectories of spacecraft, the formation of black holes, and the evolution of the observable universe.
One set of principles, across scales spanning more than 40 orders of magnitude, from planets to galaxies, from stars to black holes, from the solar system
to the cosmic web. At this point, the question has expanded far beyond the solar system. We began with Earth and the Sun. Then we followed gravity outward to planets, stars, galaxies, black holes, and the structure of the universe itself. But now we must turn in the opposite direction. Not outward, inward, toward a question that physicists increasingly believe may be fundamental. What if gravity is really about information? This idea sounds strange because information is usually associated with computers, books, and human knowledge. Yet modern physics treats information as something physical. Information can be stored, transferred, transformed, and according to many physicists, it can never truly be destroyed. This realization emerged dramatically from black hole research. For decades, black holes appeared to create a paradox. Objects could fall into them. Information seemed lost forever. But quantum mechanics strongly suggests that information must be preserved. This conflict became known as the black hole information paradox. The paradox attracted some of the greatest minds in physics, including Stephen Hawking, Leonard Susskind, and many others.
Their work eventually led to one of the most surprising ideas in modern science, the holographic principle. The basic idea is astonishing. Everything occurring within a volume of space might be describable by information encoded on its boundary. In simple terms, our familiar three-dimensional reality could emerge from deeper informational structures. No one has proven that the entire universe works this way, but the mathematics is powerful enough that many physicists take the possibility seriously. If true, then gravity may not simply shape reality. Gravity may emerge from information itself. Think about how remarkable that would be. Earth's orbit around the sun, the formation of galaxies, the evolution of stars, all of it arising from informational relationships hidden beneath spacetime. The deeper physics goes, the less reality resembles common sense. And yet, every new layer somehow explains more than the last. Another clue comes from entropy. Entropy is often described as disorder, but a more precise interpretation involves the number of possible microscopic arrangements of a system. Black holes possess enormous entropy. In fact, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This result, derived through the work of Hawking and Jacob Bekenstein, remains one of the strongest hints that information and geometry are deeply connected. The universe appears to be telling us something. Space, time, gravity, information. They may not be separate concepts at all. They may be different aspects of a deeper framework that we have only begun to glimpse. And this brings us back once more to Earth's orbit. Because even though the mathematics behind planetary motion is extraordinarily successful, the ultimate reason those equations exist remains unknown. Why should mass curve spacetime? Why should spacetime possess geometry? Why should geometry govern motion? Why should the universe obey mathematical laws at all? These questions remain open. The closer we move toward the foundations of reality, the more we encounter mysteries rather than final answers. Yet, despite these unanswered questions, the predictive power of physics is extraordinary. Using gravity alone, humanity has guided spacecraft across billions of kilometers. Scientists predicted the existence of Neptune before seeing it. They predicted gravitational waves a century before detecting them. They measured the bending of starlight. They tracked black holes. They mapped the cosmic microwave background. Again and again, nature confirmed the equations. This success reveals something profound. The universe is not random chaos. It possesses deep structure, patterns, relationships, regularities that can be discovered and discovered.
And nowhere is this more beautifully demonstrated than in orbital motion. For billions of years, Earth has followed its path around the sun.
Through asteroid impacts, ice ages, mass extinctions, the rise and fall of species, the appearance of human civilization. Through every event in Earth's history, the orbit continued. The sun rose, the seasons changed, the geometry persisted. The stability of that orbit allowed oceans to remain liquid. It allowed climates to develop. It allowed life to evolve. In a very real sense, every living thing owes its existence to the remarkable fact that Earth does not crash into the sun. But even this is temporary. Nothing in the universe lasts forever. The sun itself is changing. Every second, it converts approximately 600 million tons of hydrogen into helium through nuclear fusion. A small fraction of that mass becomes energy, according to Einstein's famous relationship between mass and energy. As a result, the sun slowly loses mass. The effect on Earth's orbit is tiny, yet it is measurable. As the sun loses mass, Earth's orbit gradually expands. Only slightly, but continuously. Billions of years from now, the sun will enter a new phase of its life. Its core hydrogen will become depleted. Fusion processes will change. The sun will expand into a red giant. Its outer layers will extend far beyond their current position. Mercury will almost certainly disappear. Venus will likely be consumed. The fate of Earth remains an active area of research. Some models suggest Earth may be engulfed. Others suggest tidal interactions and orbital expansion could produce a more complex outcome. Either way, the world we know will no longer exist. The orbit that remains stable for billions of years will eventually encounter a transformed star. And beyond that lies an even larger future. The Milky Way itself is moving toward another galaxy, our nearest large galactic neighbor, the Andromeda Galaxy. Observations indicate that the two galaxies are approaching one another at hundreds of thousands of kilometers per hour. In roughly 4 to 5 billion years, they will begin a slow gravitational merger. This does not mean stars will collide like billiard balls. Space is far too empty for that. Instead, gravity will gradually reshape both galaxies. Spiral arms will distort. Stellar orbits will change. The structure of the Milky Way will be transformed. The night sky of any surviving observers would become spectacular beyond imagination. And even this is not the end. Far beyond the era of stars, cosmologists predict a universe that becomes increasingly dark. Star formation eventually declines. Galaxies exhaust their gas supplies. Existing stars die. Black holes dominate. Then even black holes slowly evaporate through Hawking radiation. The timescales involved are almost incomprehensible.
Trillions. Quadrillions. Numbers so large that human intuition loses meaning. Yet, throughout all of those eras, one theme remains constant. Motion. Orbits. Geometry. The relationships between matter, energy, and space-time. The same principles that explain Earth's motion today continue shaping the far future of the cosmos. And so we arrive back where we began. Why doesn't Earth fall into the sun? At first, the answer seems simple. Earth moves sideways while gravity pulls inward. But beneath that simple explanation lies layer after layer of deeper understanding.
Newton revealed that the same gravity governing falling apples governs planets. Einstein revealed that gravity is geometry. Modern cosmology revealed that planetary systems are part of a cosmic hierarchy extending across billions of light years. Quantum theory hints that space-time itself may emerge from something deeper still. What began as a question about a planet became a journey through the architecture of reality. Earth does fall toward the sun. Every second. Every moment. But because space-time is curved, because motion persists, because angular momentum is conserved, and because the laws of physics possess a remarkable mathematical structure, that fall becomes an orbit. A continuous descent that never arrives. A path traced through geometry. A balance not of opposing forces, but of motion and curvature. And perhaps that is the most beautiful lesson hidden within the question.
The universe is not held together by stillness. It is held together by motion. Planets survive because they move. Stars remain in galaxies because they move. Galaxies persist because they move. The cosmos is not a static construction. It is a dynamic process, a grand unfolding dance of matter and space-time. And at this very moment, as you listen to these words, Earth continues its endless journey around the sun, traveling through space at nearly 30 kilometers every second, carried by gravity, guided by geometry, connected to laws that extend across the observable universe. A world forever falling and forever missing its target.